So section 11.8, and or the second section 11.8 rather, and we're finding areas under parametric curves. Now, with this one, we're really using the techniques from the integration by substitution part of the chapter. But if you go back and watch the video, I showed you this fact. Now, if you're happy to accept that fact, that's fine. If you are not happy to accept that fact, then go back and watch the video on integration by substitution, and I prove this to you. But this is the case. If you're integrating with respect to x, if you're integrating a function y with respect to x, and you'd like to be integrating with respect to t, well, that's fine, integrate y with respect to t, but in order to do that, you've got to throw in a dx by dt, okay? That's a thing that we've got to do. So, that's a fact, and it's easier to use it explicitly when it comes to finding areas under parametric curves. We can actually sort of do these, thinking of them as a substitution. Instead of integrating with respect to x, we want to integrate with respect to t, so we do it as a substitution for t into the equations, but it's probably easiest to just use this explicitly. So that's what we're going to do. So if we want to integrate y with respect to x from 0 to 2, then instead we're going to integrate y. Well, y we have in this example in terms of t. I'm taking the example straight from page, in my book 344a, so I'm taking this example here from the book. So y is 1 plus t. dx by dt is something I'm going to have to work out. So I have x is t plus t squared. I'm going to write it that way. So 1 plus 2t is my dx by dt. So y times dx by dt with respect to t. Now x went from 0 to 2. So what is my t going to go from and to? Well, when x equals 0, then 0 equals t plus t squared. Okay? So when x equals 0, t times 1 plus t is 0, so t could equal 0 or minus 1. Okay? When x equals 2, so t equals 0 or minus 1. I'm just going to leave that there for the moment. When x equals the upper limit, which is 2, 2 equals t plus t squared, so x equals, so t equals minus 2 or t equals 1. Now, you might think we've got a bit of a problem, because for the lower limit, t could be 0 or minus 1, and for the upper limit, t could be minus 2 or 1. But if we look carefully, it told us in the question that the parameter t has to have positive values. So it's no problem, we just need to take, sorry, not positive values, but non-negative values, 0 or bigger. So when x is 0, the t value is going to be 0. When x is 2, the t value is going to be 1. And now we've got an integral that we can deal with. Okay, so integration of parametrics, pretty similar to the substitution methods. You're going to change the variable and change the limits. You've got y in terms of t, so of course we have to do an integral with respect to t instead of an integral with respect to x. But it's probably easier to explicitly use this formula than anything else. So that's the way the book does it, and that's the way I'm going to advise you to do it. From there on, it's just a case of doing the integration. We've done all the methods now for integration, and if you want to check this one out explicitly, it's in the textbook for you. If you have my edition of the textbook, it's on page 334a after the next exercise. If you have a different edition of the textbook, then it's in the section called Areas Under Parametric Curves. Now, I should also just point out, if you have an edition of the textbook that doesn't include this section, it should be available from the publishers, because I think it was a sort of a misprint that they missed it out in the first place. But I'll leave that up to you. I'm sure your teachers can provide you with a resource that you can use. So that is the end of the integration chapter at long last. It is a difficult chapter. There's an awful lot of stuff on it. Give it plenty of time, give it plenty of practice, and good luck.